This is part 3, Perceptron, a building block of neural network of the series AI for Everyone. Enough about AI history and background. Now let's deep dive into our topic of LLMs. Here you see an image of a biological neuron, which is an inspiration for the artificial neuron known as the perceptron shown below it. The perceptron was developed in 1957 by Frank Rosenblatt as a simplified model of a biological neuron. However, a word of caution, biological neurons are far more complex and capable than perceptrons. This comparison is for reference only and should not be considered a feature-by-feature comparison. In the image, we show a single-layer perceptron with 3 inputs and 1 output for simplicity. In reality, a perceptron can have many inputs and many outputs, as we will see in the next slides. At the center of this structure is the activation function, how a perceptron works. Each input is multiplied by its corresponding weight. The weighted inputs are then summed, and a bias value is added. This sum is then passed through an activation function, which determines the final output. Mathematically, the perceptron can be represented as y equals f of x1 multiplied by w1 plus x2 multiplied by w2 plus x3 multiplied by w3 plus bias. This sum is then passed to activation function, which will produce the final output. Each input and bias in a perceptron is referred to as a parameter. In our case, we have a perceptron with 4 parameters, 3 weights plus 1 bias. You might have heard about LLMs with 100 billion or even 137 billion parameters. Now you understand what those parameters refer to. At the start of training, weights are initialized to random values. As training progresses, these weights are continuously updated based on the model's learning. Consider training a perceptron to classify images as dogs or cats. In this case, the inputs vary depending on each image fed into the model. However, the weights are updated iteratively within a single variable set. They do not change independently for each input, but are refined globally over time as training progresses. One major challenge in neural networks, including perceptrons, is catastrophic forgetting. This occurs when a model continuously updates its weights and biases, causing it to forget previously learned patterns. To mitigate catastrophic forgetting, models must be validated on diverse datasets throughout training to ensure they retain past knowledge. Smaller LLMs are more prone to catastrophic forgetting because they have fewer parameters to retain past learning while adjusting to new information. In contrast, larger LLMs, with billions of parameters, have more capacity to store information, making them less susceptible to catastrophic forgetting. LLMs are composed of many layers of perceptrons. To draw an analogy, think about logic gates in electronics. The more transistors you have, the more gates you can build, leading to more powerful microprocessors. Similarly, in the LLM world, more parameters generally mean a more powerful model, though the effectiveness depends on the quality and quantity of training data. Here is an image of a multi-layer perceptron, MLP, also known as an artificial neural network, ANN. When a neural network has more than 2 hidden layers, it is called a deep neural network, DNN. However, when there are billions of parameters across many layers, we call them large language models, LLMs. Here is an online playground where you can create your own neural network. It is limited to some of the mathematical equations only, but it will give you a feel. Our first problem is that we want to draw a boundary to separate blue dot from orange dot. Let's run it and observe. As you see, it was quickly able to learn to draw the boundary with 2 hidden layers, and graph is pretty stable. Let's pick a little more complex problem. Remember, this is all running locally within the browser. Here you can see different types of neural networks. Just like machine learning algorithms, neural networks are specialized for solving different types of problems. Choosing the right network depends on the nature of the data and the task at hand. With advancements in AI, hybrid models are continually improving, offering more powerful and efficient solutions. At the core of neural networks is the perceptron, which serves as the fundamental building block. A perceptron is the simplest type of neural network, primarily used for binary classification problems. However, it has a limitation. It can only solve linearly separable problems. To overcome this, multiple perceptrons can be arranged in layers, forming more complex architectures. These multi-layer networks allow us to solve nonlinear problems, making deep learning possible and enabling powerful applications in image recognition, natural language processing, and beyond. Neural networks have evolved over time, with each new architecture designed to overcome the limitations of its predecessors. Recurrent neural networks, RNNs, were introduced to handle sequential data, but they struggled with long-term dependencies, which led to the creation of LSTMs and GRUs. Similarly, convolutional neural networks, CNNs, improved image recognition by capturing spatial patterns, while transformers revolutionized NLP by addressing the inefficiencies of sequential processing in RNNs. Today, hybrid models combine the strengths of multiple architectures, continuously pushing the boundaries of AI capabilities. You may now ask, how is classic ML different from neural networks or deep learning? Classic ML is purely based on mathematical formulas. It requires deep knowledge about how the mathematical formulas works and which algorithm to use for a particular problem at hand. They do not use neurons or neural networks, therefore it relies very heavily on feature extraction or feature engineering. They do require training, but this training is not that intensive, as in deep learning, it does not use backpropagation. The way they learn depends on the type of algorithm, but typically they update coefficients, decision rules, or probability distributions based on the input data to make better predictions. These models usually have fewer parameters, coefficients, to update, allowing them to be optimized using direct mathematical formulas or iterative methods like gradient descent. But some models, e.g. gradient boosting, can still be computationally intensive. Here is the table that shows training requirements of different classic ML models. Here is the table showing what kind of hardware they require for training and inference. Classic ML model relies on data scientists with domain knowledge to perform feature extraction or engineering, whereas in LLM, there is no need for feature engineering or feature extraction, as LLMs are capable of automatically learning patterns from the data.